The topic of today's tutorial is neuromorphic processing at the sensor edge. In particular, how the tiny brain-inspired paradigm is translated into the modular framework and hardware platform. Let me start by stating that sensors are everywhere. We envision a world where devices, machines, cars are much more intelligent, simplifying and enriching our daily lives. Such devices will be able to perceive, reason, and take initiative actions based on awareness of the situation, improving just about any experience and solving problems that to this point we have either left to the user or to the more conventional algorithms. According to the recent McKinsey report, there will be 43 billion new connected devices per year by 2021, with each of these devices including multiple sensors. For example, your phone has on average 5 sensors per devices, Fitbit 5, your vacuum cleaner 2, a car more than 10, etc. A demand for the smart products like the fitness bands and smartwatches and smart thermostats, for example, will increase as component technologies evolve and their costs decline. We observed similar dynamic also with the rise of smartphone usage. The increase in orders coincided with a steep decline in the price of the critical smartphones components. To illustrate it with an additional example, biomedical sensors and systems, this current advancement of nanoelectronics technology coupled with higher accuracy, smaller form factor, reduced cost and increased convenience of use have enabled incorporation of a CMOS IC design in the realization of a variety of implantable and non-invasive biomedical systems, such as artificial retina, cochlear implants, deep brain simulations, vital sign monitoring, etc. These advancements in biomedical systems are main driver for the paradigm shift in biomedicine, where the focus is shifting from healing to preventing, from disease to health management, and from hospital-centered to daily life-centered medicine. To make sense of all this sensor data, we firstly analyze sensor data for the relevant patterns through feature extraction. In addition, to gain deeper insights in a particular condition, which we want to recognize, diagnose, or to quantify, data from multiple sensors is combined in sensor data fusion. Subsequently, signal recognition is performed where signals are recognized based on identified features. Sensors produce streams of data which must be processed and analyzed, which requires intensive analytics and signal processing operations. However, cloud-based processing is not feasible for the real-time, time-critical use cases and sensors generating continuous data streams. Processing is typically performed on a microcontroller or digital signal processor or a custom accelerator located with a sensor or in a separate sensor hub. Within limited power threshold, functionality achievable with conventional compute solution is significantly limited, and specialized accelerators and fixed function blocks provide a temporary respite with a higher bill of materials. However, that leaves limited compute power for the AI and deep learning based analytics. When looking at the market, we can observe that the consumer market has expanded by more than 20 times every 10 years since the 1960s. It is expected that the Internet of Things will continue the same trend as a consequence of continuous reduction in device size, reduction in power consumption, expansion in market volume, and importantly, a trend of combining emerging technologies. More specific, for artificial intelligence, IoT, features improvements will not come only from CMOS technology scaling. More innovation in the circuits, systems, and design methodologies is required. to be able to cope with very stringent power and area requirements of edge and node devices. So within this tutorial, I would like to highlight design methodology inspired by Tiny Brain to obtain competitive performance within this challenging environment. I will start with a brief overview of the conventional signal classification illustrated on an example of a biomedical SoC, followed by the brief introduction of the spiking neural networks, which are main computational concept to enable efficient pattern recognition and learning. Next, I will highlight the main design guidelines inspired by tiny brain functionality and organizational principles, with particular focus on a fully modular hierarchical time-continuous spiking architecture, and outlook at the computational units definitions. At the end, I will discuss efficiency from prediction in terms of the hierarchical perspective and evaluation, and finally give a main conclusion. So firstly, let's have a look on a conventional signal classification on an example of the biomedical system on chip. In a typical biomedical SoC, such as brain-machine interfaces, due to the small amplitude of neural signals, firstly amplification and bandpass filtering of the neural signals is performed before the signals can be digitized. An AD converter digitizes the amplified neural signals, and a low-power neural processing unit provides additional filtering and executes spike discrimination sorting algorithms. The relevant information is then transmitted to the outside receiver or can be used for stimulation in a closed-loop framework. When we compare results of signal processing blocks, in this case analog front-end and an analog digital converter, and when we compare it with a signal transmission, we can see that it costs approximately two orders of magnitude more power to send relevant information to the outside receiver than to process it on chip. What does it mean for the future outlook of the brain-machine interfaces? So, when we record action potentials, so recordings of all the signal neurons, which have the bandwidth of 10 kilohertz, and if we quantify that with 10-bit resolution at Nyquist rate, it leads to a data rate of 20 kilobits a second. For high count recording electrodes, for example 10 times 10, like the Utah electrode, it leads to a data rate of 20 megabits per second. What about power dissipation? So if we look at the typical power versus data rate graph for a body area network or personal area network, we can derive that 20 megabits per second leads to a 200 milliwatts power consumption. So a typical high density battery such as the LR44 would be empty in under an hour. Which is, especially for the implantable brain-machine interfaces, unsustainable. So our solution comprise of the data compression with on-chip neural decoding, and more specifically implementing machine learner on chip. Typically, quantized neural signals are detected with, for example, thresholding method before feature extraction is performed, with, for example, principal component analysis. Here, a typical process is illustrated with row spikes, spike alignment, and principal component analysis. We compared several classification methods, such as the Euclidean distance, Markov distance, PCA, support vector machine, and template matching. And with a particular emphasis on the overlapping spikes. We can see that the support vector machines classifier performs the best. So we have implemented cascaded multiclass SVM, cascaded so that in the most cases small number of support vector is applied instead of the entire set. In addition, we supplemented the method with model reduction techniques to reduce the amount of the required support vectors. Here we compare energy efficiency of the spiking neural network neuromorphic systems in comparison with the conventional SVM classifier. Red line designates an out-of-shelf SVM implementation. Blue is our implementation, as is shown in the previous slide. And black line represents neuromorphic implementation. As it can be seen, neuromorphic is able to obtain up to the 500 times lower energy for the same classification accuracy in comparison with the SVM implementation. Such efficiency is obtained by utilizing a multitude of factors. So firstly, the computation subthreshold analog circuits are used instead of the digital circuits operating in saturation region, and synaptic operation is based on the multi-compartment receptor implementation to increase the signal processing capabilities instead of the dot product based implementation. Also, communication is performed with event driven instead of clocked digital systems, in addition to the brain-inspired hierarchical communication between the segments. So, how is pattern recognition with spiking neural networks done? It's a fairly straightforward process. Input data, whether in an analog or a quantized or digitized form, is encoded into spikes with some of the methods. Usually, most often it's used encoding based on latency encoding, where exact timing of spikes is important. So encoding data is subsequently offered to a spiking neural network whose connections or connection strength pre-configured by the training or learning process. So generated spikes are decoded if the response of the network matches specific predefined response used for defining a specific pattern. The pattern is designated as identified. It should be noted, though, that in the end, it is the sensor system that matters, and that the system-optimized solution and SNN definition will be influenced with multitude of considerations. Among them, built-in redundancy, reliability of the sensors or sensor data, convergence towards the SNN definition, consequences of sparse representation, and access to pattern storage or retrieval. In comparison with the typical von Neumann or Harvard architecture, where there is a clear macro-level separation between the memory and computation units, which require high-speed communication bus and subsequently high power, to communicate, memory and computation elements in neuromorphic structures are highly co-localized, and signal processing is performed in a distributed event way. Spiking neural networks, as the name suggests, are based on the principle of computing using voltage spikes or neuron-generated events. Input data is encoded as the sequence of spikes, each with specific temporal characteristics. Each neuron is responsive to specific temporal sequences, which enables them to natively perform pattern recognition. as well as more complex processing. Basic principle of neuron activation is as follows. So inputs are connected to the postsynaptic neuron through weighted synapses, and the kernels acts as a hidden layer element and integrate the synaptic signals. Dendritic signals are summed at the soma, and if the signals exceeds the threshold, the axon releases spike. Spike-based computation is very powerful, and a single spiking neuron can realize the same computational performance as in an NN with hundreds of neurons. Although ANNs have proven to be quite powerful engineering tool in a wide scope of application like the pattern recognition, control, bioinformatics, robotics, etc. There are interesting limitations like the artificially designed neural model and network architecture are strongly restrictive compared to the spiking neural networks. When the first neural networks were modeled, the prevailing belief was that intelligence is based on reasoning and that logic is the foundation of the reasoning. So in the 1940s, McCulloch-Pitts designed their model of neuron in order to prove that the elementary components of the brain were able to compute elementary logic functions. So the first application of threshold binary neurons was to build networks for computing Boolean functions. So in tradition of the Turing's work, they thought that the complex or intelligent behavior could emerge from a very large network of neurons, combining huge numbers of elementary logic gates. Separately, neurobiological research has greatly progressed. Notions such as the associative memory and learning and adaptation, attention and emotions have unseated this notion of logic and reasoning as being fundamental to understanding how the brain processes information. And time has become the central feature in cognitive processing. The current consensus agrees that the cognitive processes are most likely based on the activation of transient ensembles of neurons, although the underlying mechanisms are not yet understood well. In terms of nomenclature, networks based on McCulloch and Pitts neurons as computation units are usually designated as a first generation of neural networks. While current definition of ANNs that apply an activation function with a continuous set of possible output values like sigmoid, polynomial, exponential functions are called second generation. Spiking neural networks with their temporal component are in this context third generation. Neuromorphic systems placed in an historical context of the computational devices as the next generation post-Moore's low power computing solution began in the 80s at Caltech. How do neuromorphic cognitive systems operate? So Professor Ludwig Boltzmann came out with a theory that molecules, moving matter, follow exponential distribution of energy. And that is exactly the same way that semiconductors work in transistors. So if you take a semiconductor chip and apply the signal, the electric current in that semiconductor follows this wonderful exponential. What is fascinating is that in biosystems in nervous tissue, ionic current also flows following these exponential distribution. And in fact, there is a Nobel Prize won by Hodgkin and Huxley, and they show all the nonlinear conductances in nerve axon follow these exponential functions. So, recognizing that semiconductor devices can, when operating in a subthreshold mode, follow the same physical rules as in neurons, and that this analog behavior could be used to compute with a high level of energy efficiency was the seminal insight. Equally important was recognizing that the time is an essential feature of neural network. Strong neuroscientific evidence exists that rather than the form of the action potential, it is the number of and the timing of the spikes that matter. This has been experimentally observed in the electrosensory system of electrical fish, in an auditory system of echolocating bats, or in the visual systems of flies. Neuromorphic systems have a wide-ranging application space ranging from consumer electronics and, for example, voice, speech, audio recognition and gesture recognition, autonomous robots, for example, for obstacle detection and avoidance, in automotive for object detection and recognition and low-level sensor data fusion, and in healthcare, for example, for monitoring EEG, ECG, or EMG signals. So, the main topic of the tutorial. A quest for continuous improvement in power dissipation in our battery-operated mobile world has led to the development of a wide variety of solutions. Early ones, such as scaling of the supply voltage, multi-core computing, and voltage management, are not enough. Within the energy efficient roadmap, main solution or activities include systems with some form of feedback control or adaptability, such as operating at a minimum energy point, energy proportional systems or always optimal systems, or beyond Turing concepts such as the quantum computing or stochastic computing. In this context, brain, or more specifically tiny brain, offers guidelines for both energy optimal systems and beyond Turing in non-von Neumann sense. Just for reference, brain energy consumption, mostly from moving the natrium, sodium, potassium ions across cell membranes. And the numbers include 60 picojoule per neuron spike and then 26 femtojoules per synaptic event. So, what are design aspects and guidelines of a tiny brain? How to distribute computation. To maximize efficiency, signals should be concentrated in space and time. This spatially concentrate highly active neurons or synapses in specific regions and temporally concentrate their activity. That means that activity occurs relatively rarely and in relatively few neurons, hence the principle of the sparsify. To be efficient, neural designs at all scales specialize. For example, neurosynaptic circuits are rationed for appropriate speed and a signal-to-noise ratio. Minimize varying costs. Place the most densely interconnected components close together and the more spatially connected components further apart. Analog signals are cheapest. Output can continuously match input, and analog processing avoids the physical constraints of dividing time into discrete intervals, so it can operate at high information rates. Use chemistry wherever possible, or neuromodulators just to switch behaviors. So, efficiency is maximized by containing circuits in complexes and small compartments. Use many of the many of the efficiencies above applied to the time intervals in which the statistics of the signals and varying are essentially fixed. However, as time advances, probabilities change, leading to the mismatches and inefficiencies. The best way to deal with changing probabilities is to predict what they are most likely to be in the next instant, and then use those predictions to readjust all the matches in timely and a cost-effective fashion. To maximize efficiency, signals should be concentrated in space and time. Information is concentrated at every scale. So similarly, to be efficient, neural designs at all scales specialize. How to optimize the system across the different compute stacks, ranging from application definition and algorithm implementation all the way to the system microarchitecture and the circuits and the device level. With all these omnidirectional dependencies, there is a great opportunity to engage in a paradigm shift and engage in co-design all across the compute stack so that algorithms and applications can influence the underlying hardware design and similarly the underlying hardware implementation to fit a particular application needs or constraint. Application designers and algorithm designers work towards minimizing network size for given accuracy and there would examine different topologies, evaluate network dynamics, apply methodologies such as pruning, clustering, etc. Along the similar lines, objective of circuits and systems engineers is to maximize the number of operations within the allowed power envelope. So these omnidirectional dependencies and a request to minimize energy per inference or a specific task require co-design across the compute stack. So large degree hardware software co-optimization and flexible hardware. These dependencies and optimizations are also replicated in hierarchical definitions of the neural networks. So from the very high level collaborative networks all the way towards the low-level multi-compartment definitions. When starting design process, we would like to work on a architectural level, that is the highest level that controls the performance. On one hand, we have a hardware simulator, which is able to assess the network performance, or hardware specifics, and act accordingly with a request to rewrite code or adapt hardware. On the other hand, we need full hardware-software co-optimization and a fully modular and a flexible system to unify this design process. We need to build a modular system or product. A modular system or chip, and not a single product. Everyone is planning a follow-on product. With modularity, we enable design framework and then a hardware platform which is able to mature. So such approach enables heterogeneity of computational elements and systems, but also enable a targeted reconfigurability, full programmability, and parameter adaptability. So this modularity and enabling of heterogeneity means that only the system or system definitions can be reused, and that the parts of the system can be tuned or adjusted accordingly. So important artifact is that the validation and the verification, which is a very cybersome process, can be reused on the system level. Let me go through the major components of the modular framework. Firstly, we need sophisticated software tooling. So more specifically, a full tool chain to compile SNL binaries from the Python description. We need a highly advanced mapper for optimal mapping of compositional SoC designs. We need a powerful software framework for detailed architectural exploration of the spiking neural networks, accounting for the physical effects. We need tools for high-performance mixed signal design optimization for advanced processor geometries and sensitive applications. And we need extensive models across different integration verticals and automated characterization and validation. And most importantly, we need full modular hardware platform that enable next generation of neuromorphic intelligence for sensor age. We call it time-continuous spiking architecture. Such modular framework and a hardware platform enables fast exploration of new challenges, whether in examining of potential benefits of the solution, either in terms of the competitive performance or potentially extending product capabilities, in terms of usability, in terms of optimal power performance for an application, or improving efficiency or coverage of the test solution. Let's have a quick view on the time continuous spiking architecture. Minimize varying costs. So place the most densely interconnected components close together and the more sparsely connected components further apart. So neurons from orderly maps, essentially neurons are placed in specific maps to save to save wire by reducing mutual interference that would increase the path length. So neuronal circuits segregate in specific clusters for the same reason. They form layers to minimize interference from input and output wires. Areas with the strongest interconnections locate closest together to minimize wire length, and they signal to distant circuits with reduced instructions to minimize the number of and caliber of wires. When looking at the segment definitions, one of the first questions might be, what is the neurosynaptic count required? Biology might offer the clue. C. elegans, one of the most researched creatures and subsequently the only organism which have its whole connectome completed, is able to sense light, temperature, oxygen concentration, pH levels, all the necessities of the wide range of sensing nodes for artificial intelligence IoT devices. So C. elegans have only 302 neurons and approximately 7.5 K synapses. Also, an interesting observation is the number of synaptic connections. For example, for 256 neurons, n squared number of synapses would be 64 K synapses. However, C. elegans have only 7.5 K synapses, 8.5 times less. Less synapses means low power consumption, area, noise, etc. What about computation capabilities? We can follow compute as much as possible within a single cell root, where complicating within a cell economize the numbers paradigm. Alternatively, we can specialize the neurosynaptic number and function according predefined goal, such as specific signal processing functions and encoding scheme, specific data rate, frequency, band of interest, feature set or complexity, target, SNR, time constant, or any other different definition. Each of the segments is fully programmable, highly reconfigurable and adaptable engine capable of real-time inference. Segments can be configured to implement a multitude of the network topologies, such as the feed-forward and current networks, where each of the signal processing neurosynaptic components can be directly controlled on chip. Modern deep learning architectures typically consist of multiple layers, where each layer consists of vector matrix multiplications followed by the specific nonlinear activation function. Performing efficient matrix computation in traditional digital computing platform poses a significant challenge as computation complexity grows quadratically. Analog crossbar arrays inherently realize the dot product operations in analog domain by applying a vector of voltage signals to the rows of synaptic crossbar. Multiplication by each synapse is performed by the Kirchhoff's current rule, and the current is summed across each column. This postsynaptic current denotes the multiplication result, and it's obtained with one designated time constant. Typical synaptic synapse implements a dot product of weights and input signals based functionality. Multi-compartment synapse includes receptor-based functionality. So the AMPA receptor is used to drive the soma, and the NMDA receptor functions as the presynaptic part. The postsynaptic part consists of the sum of the two influences, and that is the dendritic spikes plus back-propagated spikes, which rise from dendrite or soma respectively. So such implementation allows a wide range of temporal behaviors, as each receptor can operate on a different temporal scale and obtain high noise tolerance, as the capability of the network to perform pattern recognition even in a noisy signal increase. Increasing the number of receptors, M improves signal noise ratio by the square root of M. So small synapse clusters with about 20 synaptic receptors improve signal noise ratio compared to one receptor by approximately 4.5 times. A large synapse receptors may expand the receptor clusters up to about tenfold. And thereby improve signal noise ratio by about 14-fold. So a note caution. However, since it comes with the tenfold greater cost, it is reserved for special purposes. For example, synapses that transmit with a high temporal precision. For the optimal allocation of resources, we can engage noise resources equation. That means trading power and area to reduce thermal or flicker noise. As additional design know-how, if noise is to be minimized, more resources should be distributed to the parts of the system that affects all other parts of it. So the initial stages, and to those parts of the systems that are complex, so the parts with high N. Now let's have a look on the neuron models. A typical neuron consists of a cell body, soma, dendrites, and a single axon. The soma is a compact structure, and the axon and dendrites are filaments extruding from the soma. The dendrites typically branch profusely and extend a few hundred micrometers from the soma. Most neurons receive signals via the dendrites and soma and send out signals down the axon. At the majority of synapses, a signal cross from the axon of one neuron to a dendrite of another. However, synapses can connect an axon to another axon or a dendrite to another dendrite. Hodgkin and Huxley performed experiments on a giant axon of the squid and found three different types of ion current: sodium, potassium, and a leak current. Specific voltage-dependent ion channels, one for sodium and another one for potassium, control the flow of these ions through the cell membrane. The leak current describes other channel types which are not described explicitly. This complex model produced realistic variations of the membrane potential and the dynamics of the spike firing. Here we can see a visualization of the neuron axon potential run on excuse me. Run on the Vertex 7 FPGA for 1 second brain stimulation time with associated neuron parameters in a biologically accurate neural network consisting of the 768 extended Hodgkin-Huxley neural cells. Simulating identical network settings in System C requires 59 minutes of the CPU time on a system with the Intel Xeon 3.5 GHz processor and 32 gigabit of memory. Consequently, an FPGA port design yields more than 3,500 speed up performed in real time. Observed difference is negligible, and that's also for the cell resting state, when most internal cell variables change rapidly for both 32 and 64-bit configurations. The response of the network consists of a series of spikes separated by long or short intervals. This arrangement of short, long, or very long interspike intervals defines the neural firing pattern. Adaptive, nonlinear, leaky integrated fire model describe a variety of firing patterns, bursting, toning, delayed, etc. A single equation is, however, not sufficient to describe the variety of firing patterns that neurons exhibit in response to a step current. The model therefore coupled the voltage equation to abstract current variables, Wk, each described by linear differential equations. So we said previously that to maximize efficiency, signals should be concentrated in space and time. This model certainly enables it. Various choices are possible for the nonlinearity f in the voltage equation. Here is one example where a nonlinearity consists of the linear leak combined with the exponential activation form. The most simple model, leaky integrated fire, where the neuron dynamics is described by linear differential equations. Here, shape of the action potentials is negligent. Spike is considered as the uniform event defined only by the time of its appearance. An alternative to dynamical systems models are so-called spike response model. In SRM, the membrane potential is not computed through a differential equations, but as a sum of the integral kernels. In this view, a neuron, also including its incoming synapses, acts mathematically as filter or operator in that it maps incoming sets of spike trains into an output spike train. In this definition, voltage across the membrane is expressed as this formulation, where alpha is the kernel describing the evolution of the postsynaptic potentials, f is the firing rate, w is the neural connectivity matrix, and t is the time of firing. E, he designates here excitatory, shown here in graph with the blue lines, and I stands for the inhibitory in graph illustrated by the red lines. The part on the integral can be defined as a synaptic drive, and kernel alpha is an exponential decaying function with the gain b. Capturing the neuroelectronic behavior of biological excitatory and inhibitory neural networks can be written as the derivative of the synaptic drive. Weight bounding can be expressed as is shown here, where probability P is based on the entropy system total certainty. Using the diffusion approximations, the neural dynamics model is fully described by the eta system of stochastic differential equations, where S is the synaptic drive at the time t with noise amplitudes sigma s of t, and omega is the independent standard Brownian process. To simplify simulation and calculations, we can approximate fx, for example, by the smooth rectification function, or like this function to model a saturation in a membrane potential firing rate curve, which might occur and at higher voltages. The time series representation of the neural signal is composed of a spike burst plus additive Gaussian white noise, gray area with 1,000 randomly selected neuron channels, compartments, and a black area with a filtered out predicted bias from the estimated variance. Similarly, we show here how spiking neural networks responds on the specific features that are detected, extracted, and encoded in the spike trains. The final section is efficiency from prediction, hierarchical perspective, and evaluation. This table illustrates variability effects along the physical dimension axis from a global IC level all the way towards the local variations on transistor or atomic level. Variations on the level of an integrated circuits are normally considered as standard design space variables, usually included in PVT models. The variations that affect subcircuits are less commonly incorporated in models and design software. Often the only mechanisms available to designer is a set of the design rule checks or electrical rule checks. Most effects at the transistor level are well modeled, as a transistor is the focus point of a circuit modeling. An increasing number of transistor-related and atomic scale effects become relevant in nanometer devices. Most of these effects are well described and modeled in physics on a micrometer level, but the associated statistical effects are not an integral part of the design flow. Here we can see a subdivision of the variability effects in static, slow, medium, and fast changing events. This subdivision is linked to the methodologies a designer has available to mitigate performance loss or yield loss. Following the same analogy, plasticity mechanism is in the brain take place at different time scales and subsequently across different integration verticals. Short-term plasticity operates over milliseconds. It includes both adaptive neuron behaviors and models as shown a couple of slides ago, in a particular calcium component neuron frequency adaptation mechanism, as well as short-term synaptic adaptation. Long-term plasticity mechanism operates over tens to hundreds of milliseconds and covers spike-based plasticity rules. And third, homeostatic plasticity operates over tens to hundreds of seconds and allows scaling synaptic weights to stabilize the neuron firing frequency ranges and thus the network activity. Finally, structural plasticity operates over days to modify the network connectivity. It is usually applied to modify network connectivity. Along the similar lines, compensation can be performed on different levels in both time and space and across different framework modularity, along the different compute stack on a circuit level, system, and architecture level, across hardware and the software lines. Here is one example of the sizing of the neurosynaptic components with a tool to achieve specific yield targets. This enables circuit design to address physical issues early in the design process. Similarly, different optimization algorithms are applied to examine different power-area trade-offs. Here is one example of bounding of the network activity by adapting control parameters of neurosynaptic implementations. At sufficiently high levels of heterogeneity, for example, increased heterogeneities in neurosynaptic parameters like integrated capacitance, firing threshold, refractory period, the network demonstrates a spatially disordered pattern of neural activity. If network activities profiles are narrow, the need for homogeneity in the distribution of spatial stimuli encoded by the network is increased. To examine the dynamic regulation of the network following activity alterations, we either eliminate activity by obstructing generation of action potentials with the voltage gate NMDA channels, or increase network activity by blocking inhibitory conduction with the GABA receptor. Control parameters are based on the interspike interval as shown here. Another example is shown here, where frequency content for a synchronous and asynchronous case is examined, and then the consequently correlation and coherence recorded. Finally, we can identify regions of the neural activity based on well-defined target features to be extracted. Here we can see different spiking behavior based on the noise level in the network in comparison with clean audio recording without background noise. For the real-time spoken word classification, less than 500 spike events are needed. The network itself is very small. It comprises of 116 to 610 neurons in total, organized in two-layer fully connected feed-forward network. For comparison purposes, time-continuous spiking architecture has 40 times lower inference latency compared to conventional DSP, and up to 49 times lower inference energy compared to the emerging ANN accelerators. So to conclude, energy efficiency is, besides security, cost, technological limits present by the end of Moore's law, one of the most important present and future challenges. High level of understanding and a more on-chip machine learning and onboard intelligence will result in moving some computational tasks that are traditionally performed in the cloud to be moved into sensor nodes, and whenever this achieves a more favorable balance between the reduced wireless data rate and the increased computational effort performed in the sensor node. Neuromorphic computing offers excellent opportunity for the energy efficient on-edge inference, and it offers an attractive solution for numerous energy-constrained applications of embedded computing, ranging from autonomous miniature robots to implantable neural prostheses. In addition to the energy efficiency, wide-ranging and fully capable modular computational platforms need to encompass several important features, among others highly advanced software compilation, network mapping and simulation, a fully programmable system fabric with fine-grained parametric control, modular multi-segment architecture with spatio-temporal computing units, ultra-efficient interconnect, highly capable neurons, and then self-adapting synapses. So finally, I would like to acknowledge amazing engineering team at Inatera Nanosystems for the contribution of some of the work presented here. Thank you for your attention.